everyone, welcome back to the channel. I'm Mist Rain. Have you tried the recently released anime-style game, Neverness to Evernness, or NTE? While playing it, I noticed quite a few technologies that used to feel exclusive to AAA titles, such as DLSS 4.5 and ray tracing. You can really tell the developers put a lot of effort into building this anime-inspired modern city. But in the NTE community, I have also seen many players talking about optimization, especially the heavy performance cost. After spending some time with the game myself, I think a large part of that cost comes from the lighting mode. So today, let's take a closer look at the 4 lighting modes in NTE, how they differ and how much they actually change the visual experience. First, let's start with SSR, the mode with the lowest performance cost and probably the one most players choose. SSR stands for Screen Space Reflections. The basic idea is simple. It only uses pixel information that has already been rendered on the current screen, then searches for reflection points through ray marching. As you can clearly see in the footage, only objects that are visible on screen can be reflected correctly. Anything outside the screen has to be faked with a texture, which is why the reflection can look completely different from the actual scene. In essence, SSR is still a fake reflection technique. It is a visual trick. The obvious seam in the mirror and the buildings that do not match the real environment are caused by the use of pre-baked reflection textures. Next, let's look at Lumen, Unreal Engine's own lighting technology. Lumen is UE5's built-in solution for dynamic global illumination and reflections. It combines several techniques, including screen space traces and software distance field tracing. If you have an RTX GPU, it can also optionally use hardware ray tracing. At its core, Lumen is a real-time system that approximates the behavior of real light. Surface cache pre-captures information about scene surfaces so lighting can be queried quickly. Screen traces prioritize information that is already visible on the screen, which makes them somewhat similar to SSR. Distance Field GI uses distance fields instead of actual geometry for ray intersection tests, then combines a limited number of RT rays with denoising. Unlike path tracing, it does not rely on massive sampling. This makes Lumen a middle ground solution. Better quality than traditional lighting, but less expensive than full ray tracing. In the footage, we can still see some incorrect texture information on the mirror surface, and the reflections have a slightly smeared look. The character also does not appear in the reflection. Even so, both the lighting and reflections are noticeably better than SSR. And some buildings, such as the DSD toy store, can already appear in the mirror. Now, let's step into the world of ray tracing. At the moment, the ray tracing techniques used in games can generally be divided into 2 types, ray tracing and path tracing. In NTE, path tracing is called panoramic ray tracing. Back in elementary school physics class, we learned that light starts from a light source, bounces around the world, and eventually enters our eyes or a camera. Only then can we see or record the surrounding scene. But if we simulate light this way directly, most of the rays are wasted. Only a tiny fraction actually reaches the camera sensor. The result is physically accurate, but the amount of computation is enormous. This is why in film production, rendering a single frame can sometimes take minutes or even hours. Games usually use a different approach. Instead of tracing rays from the light source, they send rays out from the camera. Test those rays against the real triangles in the scene, and then simulate how the light bounces. No matter which ray tracing method is used, the pipeline usually includes these steps. The camera first emits primary rays, which intersect with scene geometry. Then the renderer calculates the material and lighting information at the hit point, generates the next bounce direction, and uses probabilistic termination to keep the result physically reasonable. This process continues while contributions are accumulated. Multiple samples are taken to reduce noise, and the final image is cleaned up through denoising. As for the math behind it, Monte Carlo integration is the core integration method used in ray tracing. The 2 most expensive parts, ray triangle intersection and BVH traversal, rely on acceleration from RT cores on RTX GPUs, or equivalent hardware on RDNA 2 and newer GPUs. This is why we often call it hardware ray tracing. Because ray tracing requires such complex and massive integration and intersection calculations, real-time ray tracing pipelines in games are still mostly practical on high-end GPUs. If you want to learn more about ray tracing algorithms in depth, I recommend checking out Josh's channel and his video. I will also put the link in the description. Finally, let's talk about the difference between ray tracing and path tracing. Regular ray tracing usually only calculates 1 or 2 light bounces. Most games that claim to support ray tracing today fall into this category. Some effects are ray traced, while the rest of the image is still rendered through rasterization. Even with this hybrid approach, the GPU cost is already very high. Path tracing is more like the complete version of ray tracing. It sends a large number of rays from every pixel and simulates many diffuse light bounces. It is currently the closest in-game rendering algorithm to physical reality. Caustics, indirect lighting, and soft shadows can all emerge naturally. It does not need the same kind of fake patchwork techniques. But the price of that realism is brutal performance cost. To run in real time, path tracing usually needs DLSS plus ray reconstruction. By the way, here's some good news. NVIDIA has officially announced that DLSS 4.5 ray reconstruction will roll out to all GeForce RTX players this August, improving image quality in ray-traced and path-traced games. For players who love ray tracing, that means we may finally stop having to choose between shimmering noise and blurry denoising. After all that, let's sum it up in a few simple lines. SSR reflects whatever is already on screen. Anything outside the screen is gone, so the game has to rely on pre-baked textures. Lumen is part of the UE5 toolkit. It is a fast, practical, and visually convincing middle ground solution. Ray tracing uses physically based light behavior, but usually only calculates 1 or 2 bounces. Some effects are ray traced, while the rest still uses rasterization. Path tracing is the ultimate version of ray tracing. It can deliver film-level visuals, but it is extremely demanding on GPU performance. Finally, let's compare these 4 lighting algorithms using real in-game footage from NTE and see how different they look in practice. Before the video ends, I want to ask, which lighting mode do you prefer? Feel free to share your thoughts in the comments. Thanks for watching. I'm Mist Rain, and I'll see you in the next video.